Good morning, everyone. I am delighted to welcome you all today. Today's presentation is focused on the qualification of refractometers, specifically highlighting Dr. S.K. Singh, PhD. I'm excited to take you through this topic, which is essential for understanding how these important instruments work. Over the next few slides, we will explore the basics of refractometers, their significance, and the qualifications needed to operate them effectively. Let's get started. Let's start with the basics. A refractometer is a handy instrument that measures the refractive index, or RI, of liquids and solids. Now, the RI is a key property because it helps us identify substances, check their purity, or determine concentrations, like how much sugar is in a solution. It's a versatile measurement that plays a vital role in many industries. But just having a refractometer isn't enough. We need to ensure it's properly qualified. That means verifying that it's accurate, precise, and meets all necessary regulatory standards. This qualification process is essential to make sure our measurements are reliable and compliant with industry requirements. So, understanding how to use and qualify a refractometer properly is fundamental to maintaining quality and consistency in our work. Let's take a closer look at the principle of the refractometer. At its core, this device measures the refractive index of a liquid, which is essentially how much light bends as it passes through the sample. This bending, or refraction, is directly related to the sample's composition, like sugar content in a solution. When light enters the sample, it slows down and bends depending on the density of the liquid. The refractometer captures this bending and converts it into a reading, usually displayed as a refractive index or a simple scale. This is why refractometers are so useful. They give us a quick, accurate way to assess concentration without needing complex laboratory procedures. Understanding this principle helps us see how the device ties into our overall goal: to efficiently analyze and monitor the quality of various liquids. Whether in food, beverages, or even in scientific research, the core idea is that the degree of light refraction reveals a lot about what's inside the sample. So, in essence, it's all about using the physics of light to get precise, real-time measurements. Let's take a moment to look at some important references that guide our quality and validation processes. First, we have USP 831, which covers the refractive index, a key parameter in many analytical methods. Then, there are the USB general notices, which provide general principles that ensure consistency across tests and methods. Moving on, ICHQ2. R1 is crucial because it outlines the validation principles we follow to ensure our analytical procedures are reliable and fit for purpose. We also rely on the WHO TRS for guidance on analytical instrument qualification, making sure our equipment performs accurately and consistently. Additionally, standards like ISO 9001 and ISO 17025 set the framework for quality management systems and laboratory competence, respectively. Lastly, EU GMP Annex 15 specifically addresses the qualification of facilities and equipment, another critical aspect to maintain compliance and quality in our operations. All these references work together to create a robust foundation for quality assurance, validation, and compliance in our processes. They ensure that everything we do meets the highest standards and helps us deliver safe, effective products. Today, I want to focus on the core aspects of routine quality control, specifically IQ, OQ, and PQ. These are essential steps in ensuring that our instruments are functioning correctly and consistently over time. Let's start with the instrument qualification lifecycle, which provides a structured approach to validating and maintaining our equipment. The first stage is design qualification, or DQ, where we ensure that the instrument's design meets our intended use and specifications before it even arrives. Next is installation qualification, or IQ, which verifies that the equipment has been installed correctly according to the manufacturer's instructions and our requirements. Following that is operational qualification, or OQ, where we test the instrument to confirm it operates properly within specified parameters during normal use. Finally, we have performance qualification, or PQ, which demonstrates that the instrument performs reliably and consistently in real-world conditions over time. Together, these stages form a comprehensive life cycle that helps us maintain quality, compliance, and confidence in our instruments throughout their operational life. This structured approach is vital to our overall quality assurance strategy, ensuring that every piece of equipment contributes to accurate and reliable results. Now, let's talk about installation qualification, or IQ for short. The main goal here is to verify that the instrument has been installed correctly. This is a crucial step because proper installation sets the foundation for reliable operation and accurate results. When we perform IQ, we check several key points. First, we verify the instrument model and serial number to ensure we're working with the right equipment. Then, we look into the manufacturer's specifications to confirm everything aligns with what's recommended. Next, we assess the power supply and the environment where the instrument is installed. It's important that the power supply is stable and meets the required standards, and that the environment is suitable, things like temperature, humidity, and cleanliness. Another critical aspect is the installation location itself. It should be vibration-free and temperature-controlled to prevent any external factors from affecting the instrument's performance. Finally, we confirm the availability of standard operating procedures and manuals. Having these documents accessible ensures that operators know how to properly use and maintain the equipment. The acceptance criteria for IQ are straightforward. Everything should be in accordance with the manufacturer's recommendations. Ensuring these points are checked and verified helps us maintain quality, consistency, and compliance throughout our processes. Now, let's take a closer look at the operational qualification, or OQ, parameters as outlined in USP 831. These are the critical aspects we need to verify to ensure our instruments are performing reliably. First, we have temperature accuracy, which is essential because many measurements depend on precise temperature control. Next, we have refractive index accuracy, a key parameter when working with optical instruments, making sure our readings are correct. Then there's linearity, which, where applicable, helps us confirm that the instrument's response is proportional across the measurement range. We also need to check repeatability, meaning that the instrument can produce consistent results under the same conditions over multiple tests. Lastly, resolution, especially relevant for digital instruments, refers to the smallest change they can detect. These parameters collectively ensure our equipment is performing within the expected limits, which is fundamental to maintaining quality and compliance throughout our processes. Now, let's discuss the temperature accuracy test, also known as the operational qualification, or OQ. This test is crucial because the RI, or refractive index, is highly dependent on temperature. Small variations in temperature can impact the accuracy of your measurements, so ensuring your instrument is properly calibrated is essential. The procedure begins by setting your instrument to a standard temperature of 20 degrees Celsius, which is the USB standard. Next, you'll measure the temperature using a certified thermometer to ensure accuracy. It's important to record both the displayed temperature on your instrument and the actual temperature from the certified thermometer. The acceptance criteria typically allow a variance of plus or minus 0.1 degrees Celsius, or whatever the manufacturer specifies. For example, if you set the temperature to 20 degrees and observe 19.9 degrees, that falls within the acceptable range, and you can consider this a pass. This test helps us verify that our instrument is performing accurately at the standard temperature, ensuring reliable and consistent measurements in our overall process. Let's discuss the refractive index accuracy test. For this test, we rely on certain reference standards, which are outlined by the USP. These include distilled water, as well as certified RI liquids and sucrose solutions. These standards are crucial because they serve as our benchmarks for accuracy. The procedure involves measuring the refractive index at a controlled temperature of 20 degrees Celsius. It's important to keep this temperature consistent, as refractive index readings can vary with temperature changes. Once we've measured the RI, we compare our results with the certified value provided by the standard. Now, the key point here is the acceptance criteria. The measured RI should fall within plus or minus 0.0002 RI units of the certified value. Some manufacturers may have slightly different specifications, so it's important to know and follow those as well. Overall, this test ensures that our refractometers are providing accurate and reliable readings, which is essential for quality control and consistency in our processes. By regularly performing these accuracy checks, we maintain confidence in our measurements and uphold the integrity of our results. Now, let's talk about the repeatability, or what we often call precision, test. This step is crucial because it helps us understand how consistent our measurements are when we repeat the same process multiple times. Essentially, we're checking if our method can reliably produce similar results under the same conditions. A high level of repeatability means our process is stable and dependable, which is vital for ensuring the quality of our data and the integrity of our overall analysis. If we notice significant variations, it indicates that there might be some inconsistencies or uncontrolled variables affecting our results. Connecting this to the bigger picture, conducting repeatability tests helps us identify potential issues early on and improve our measurement procedures. Ultimately, this strengthens the reliability of our entire testing process and supports better decision-making moving forward. Now, let's talk about the linearity test. When we're evaluating the method's performance, we start with standards, which in this case are sucrose solutions at different concentrations, such as 10%, 20%, and 30%. These standards help us determine if our measurement system responds proportionally to changes in concentration. The procedure involves measuring the refractive index, or RI, for each of these concentrations. Once we have those readings, we plot the RI values against the corresponding concentrations. This visual representation allows us to see whether the response is linear, meaning directly proportional. The key acceptance criterion here is the correlation coefficient, or R. We want this value to be at least 0.999, which indicates an almost perfect linear relationship. Achieving this level of linearity confirms that our method is reliable for quantifying sucrose concentrations accurately across the tested range. This step is essential because it ensures that our measurements are consistent and dependable, which ties into the overall theme of method validation. A linear response gives us confidence that the method can accurately reflect concentration changes in real samples. Now, let's talk about performance qualification, or PQ for short. The main goal here is to verify that our process performs consistently during routine operations. This is done using actual samples, which really helps ensure that what we're testing reflects real-world conditions. The frequency of PQ can vary. Some checks are done daily, others weekly or monthly, depending on what's most appropriate for each specific process. It's important to use system suitability standards during these checks, as they serve as benchmarks to confirm that the system is functioning properly. Some typical checks we perform include the water RI check, which helps verify the water quality and consistency. We also do control chart trending, which involves plotting data over time to identify any shifts or trends that might indicate a problem. These checks are crucial because they help us maintain quality and consistency in our performance, tying back to our overall goal of ensuring reliable and compliant operations. Remember, routine PQ is about catching issues early and confirming that everything remains within acceptable limits. Let's talk about documentation, which is a crucial part of our process. First, we have IQ, OQ, and PQ protocols and reports. These stand for installation qualification, operational qualification, and performance qualification. They help ensure that equipment and systems are installed correctly, functioning properly, and performing as intended. It's important to have detailed protocols and reports for each stage. Next, calibration certificates are essential to prove that our instruments and equipment are calibrated accurately and regularly. This maintains the integrity of our data and processes. Moving on, raw data and calculations are the backbone of our documentation. They provide the evidence needed to verify our results and support our conclusions. Then, we have deviations and CAPA, or corrective and preventive actions, if any issues are identified. Documenting deviations helps us understand what went wrong, and CAPA ensures we address root causes to prevent recurrence. Overall, thorough documentation supports compliance, traceability, and continuous improvement, which are all key themes in our quality management approach. Let's wrap up with the key takeaway from this presentation. A qualified refractometer plays a crucial role in ensuring reliable results, which means you can trust the data you're getting. It also helps maintain regulatory compliance, making sure your processes meet industry standards and legal requirements. And of course, it safeguards data integrity, so the information you rely on stays accurate and unaltered. In essence, choosing the right refractometer isn't just about measurement. It's about supporting quality, compliance, and trust in your operations. This ties back to our overall theme of precision and reliability in your testing processes. For further support, please don't hesitate to reach out to us. We're here to help you with any questions or additional guidance you might need. Thank you so much for your time and attention today. We truly appreciate your engagement and look forward to assisting you further.